Okay, video 3, extrinsic conduction. So the definitions are here. Extrinsic conduction is conduction in a doped semiconductor. In other words, we're taking a semiconductor material and adding an impurity to it. So impurities are added to the semiconductor material to increase its conductivity. Now there are two types. There are p-type semiconductors, where an impurity is added such that there are more positive charge carriers available for conduction. In other words, there'll be more positive holes available as the majority charge carriers. And then there are n-type semiconductors, where electrons, which are negative, are the majority charge carriers. And there's a different material that's doped to get an n-type semiconductor in comparison to a p-type semiconductor material. Okay, so let's start with the n-type. Remember, n-type has more electrons, or has plenty of electrons available for conduction. So they're doped with phosphorus. You need to remember this. Phosphorus is an atom that has 5 electrons in total. And as a result, when it bonds with the silicon, there's 1 electron left over. And that electron left over is available for conduction. Let's have a look at it in more detail. So we have a silicon atom there. There's a covalent bond. And if you dope it with phosphorus, some of those silicon atoms can be replaced with a phosphorus atom. Okay, so remove a silicon, put in a phosphorus atom. But the thing is, the phosphorus has an extra electron. More electrons here now mean that we'll have more electrons available for conduction. As a result, the resistance of this thing is dropped automatically because the conductivity is increased. So that electron is not bonded, so it's free for conduction. Now if you do it again, dope it some more, we have more electrons available for conduction. So again, the conductivity is increased. Phosphorus in this case is called the dopant. It's the element that's added to increase the conductivity. Let's apply a potential difference across it. And then what would happen here is the electron would travel to the positive terminal or positive plate. As a result, there's a current flowing. Okay, so the n-type semiconductor there, it's n-type because there's majority charge carriers are negative electrons, and as we add energy, you will have electron-hole pairs. It's just that you'll have more electrons than you will holes, which is why we call it an n-type, because they're majority charge carriers. So there's more of them than the positive holes. All right, and the last sentence there is probably the most important thing that you need to remember. The silicon is still electrically neutral because there's an equal number of protons and electrons in that substance. So while I've added an extra electron for each phosphorus atom, the phosphorus atom also has an extra proton in comparison to the silicon, so it's still electrically neutral. Right, that's what we're going to show the n-type as from now on. Okay, second type, p-type. This is what you need to know. P-types are doped with boron, and boron atoms have 3 electrons in their outermost shell, so you're going to be missing an electron when you dope silicon with boron. All right, so same idea. Remove silicon, put in boron. And because we're missing an electron, or there's a gap where an electron should be, we'll have a positive hole. Much like the previous one, the majority charge carriers here are going to be positive holes, which is why we call it p-type, but it's still electrically neutral. So you can read the text as we go. Okay, we've doped it further, and as a result, we've increased the conductivity of the medium. Boron, in this case, is the dopant. It's the impurity added. Okay, apply a potential difference across it, and what will happen here then is electrons will fill the holes, and as a result, we'll think the hole is actually going to the right, but what's actually happening is the electrons are going to the left as they fill the holes. And electrons will fill the hole, leaving a hole behind, and then another electron will fill that hole, leaving a hole behind, and this repeatedly happens. So we think the hole is traveling, but in actual fact the electrons are going in the opposite direction. Okay, so the p-type semiconductor, it's called p-type because the majority charge carriers are positive holes, but there are positive holes and negative electrons as charge carriers in this material. It's just that there are more positive holes as charge carriers. which is why we call it p-type. And still electrically neutral. This is how we look at the p-type in the next video.